Suyu. She did her PhD at Caltech with Roger Blanford, also on strong energy, actually in Cosmography. And now she's in Bonn since 2 years, and she's going to tell us about the Hubble constant and how you can measure that with some nice lensing.
Thank you very much for having me here. So I'll tell you about precision measurements of the Hubble constant, flatness parameter, and the dark energy equation of state from the gravitational lens 1608 plus 656. Here's a quick outline of my talk. So the first one is on the main title, or there's a short title, Cosmography from 1608. I will describe the motivation and give a brief introduction to lensing. I will explain what the mass sheet degeneracy is and how we break it. I will outline the probability theory for combining the multiple data sets we have on 1608. And finally, present the measurement of cosmological parameters from 1608. In the second part of my talk, I will tell you about the size of a galaxy dark matter halo in SL2SJ0854 and the rest of its phone number. I'll give a brief introduction, describe our method for measuring the halo size, and show you some preliminary results. So one of the key questions in cosmology now is, what is the nature of dark energy? Is it a vanilla cosmological constant with W is -1? Is W time varying? One way to make progress on answering these questions is a precise measurement of the Hubble constant, because as Wayne Hu pointed out in 2005 and recently shown by Reese et al. And collaborators, H0 is the single most useful complement to the CMB parameters for dark energy studies. H0 is also important in its own right because it sets the age, the size, and the critical density of the universe. Recent measurements of the Hubble constant in these units are the HST key project of 72 plus or minus 8. This is based on secondary distance indicators such as type 1A supernovae, Tully-Fisher, surface brightness fluctuations that are calibrated using Cepheid distances to nearby galaxies with a 0 point at the LMC. WMAP's 5-year results give very tight constraints, 71.9 plus 2.6 minus 2.7, assuming flatness and that W is -1. Recently, Reese et al. Obtains using a differential distance ladder of H0 is 74.2 plus or minus 3.6. I note that the key project is dependent on the distance ladder, which is prone to systematic effects such as the period luminosity relation of the Cepheid depending on the metallicity. The tight constraint of WMAP assumes flatness and that W is -1, and if either of these assumptions is relaxed, the uncertainty in H0 increases. For example, here, if I relax flatness, the constraint on WMAP is shown here, where the Hubble constant can vary between coordinates. Since H0 is an important parameter, it's useful to measure it using a full range of methods, and one alternative is gravitational lensing.
How do these measure the H0? Type 1A?
It's also type 1A, but it's based on differential distance ladder where the 0 point is at the major galaxy. Here are 2 examples of gravitational lensing. Here is the galaxy cluster AGAL 1689. The yellow-orange things you see here are the cluster members. If you look closely, you can see giant arcs. These are background galaxies being gravitationally lensed by the foreground cluster so that its images are highly distorted and sometimes split into multiple images. Here and here. This is the case of strong lensing, where you get multiple images of the same source. In the outskirts, you have weak lensing. So, for example, a circular source may be distorted so that it appears to be an ellipse. In my talk, I will focus on strong lensing, that is where you have multiple images of the same source. Here is an example of a strong lens at galaxy scale. The background source is lensed into 4 images, 1, 2, and the third and the fourth are merging, 3 and 4, by a massive foreground galaxy, the SLAC lens J0737. You can actually make your own strong lenses at home. If you have a candlelight, you you put the base of a wine glass in front of it, you can strongly lens the light into multiple images. Shown here. You have three, there's a fourth one that's behind the dim, so you can't really see it. The morphology of this configuration is actually very similar to the strong lens that you saw here. And by tilting the base of the wine glass, you can have different geometry. For example, when you have the base of the wine glass face on, perfectly aligned with the candlelight, you get a perfect ring. This is called the Einstein ring. And the radius of the circle is the Einstein radius. Tilting it slightly from that, you can get two images. So various tilts correspond to, or analogous to, different ellipticity of the lens galaxy. Let us now look in detail at how lensing works in theory. This is the source plane, the image plane, and we, the observer, here. Coordinates on the source plane is beta, on the image plane is theta. Light ray from the source gets deflected so that it appears to be here instead of here. The equation governing the deflection of light ray is the lens equation. Very simple. Beta is beta minus alpha, where alpha is the scale deflection angle, that is the gradient of the lens potential psi that describes the mass distribution. The lens potential is related to the surface mass density. This is the projected mass density along the line of sight to the source, kappa, by the Laplace equation here, half the Laplacian of the lens potential. In the case of strong lensing, we can have another light ray reaching us so that we see this image in addition to that one. The deflection of light ray is, so lensing is sensitive to the total mass distribution of the lens. By modeling the image configuration, the image position, image shapes, we can infer the total mass distribution of the lens. By comparing this to the luminous parts of the lens that we observe, we can use gravitational lenses to infer about the dark matter properties of galaxies. And so lensing provides dark matter probe. In special cases where the source is time varying, we can see time delays between multiple images. The time delay, the excess time delay relative to the case of no lensing is given here. There's some prefactor, and there's two pieces. There's a geometric part that's due to the path difference between the two light rays, and then a potential part that's due to the Shapiro effect. The coefficient here, the distance ratio in 1 plus d, d is the deflector of the lens. I call this the time delay distance, d delta t, and it's inversely proportional to the Hubble constant. So the distance here is marked here. D refers to deflector, source, and the distance between deflector and source. So, if we have a strong lens, a time delay strong lens, and by measuring the time delay between the multiple images, modeling the lens, the image configuration, we can use strong lens systems to do cosmography by constraining the time delay distance. 1608 is such a time delay lens. Here is the image, an 8th observation. The background source is lensed into images A, B, C, and D at this redshift 1.39 by two interacting galaxies, G1 and G2, at the redshift of 0.62. The relative time delays between the four images have been accurately measured with errors of only a few percent. So as you can see in this UBCS image, the extended sources provide additional constraints on the lens potential. So we have this part and this part, so which means 1608 provides a good opportunity to measure the time delay distance with high precision. The caveat is we have to model the lens potential accurately. I don't want to go into the details, but we do so by describing the two galaxies as elliptical power law profiles with slope gamma prime. And then on top of that, we have pixelated correction to take into account that these two interacting galaxies may not be well described by simple elliptical mass models. What we find, however, is that the pixelated corrections are very small, only on the order of 2%, and that the simple elliptical power law models for the two galaxies actually provide an accurate description of the system. So we have time delay. We also have the accurate length potential. That's the Fermat potential here. We're in business to get the time delay distance. Well, not quite, because of Massey degeneracy. What is the Massey degeneracy? Let us first consider the galaxy profile described by the dotted line here. Suppose we do a transformation of the surface mass density by adding a constant sheet of mass and rescaling the galaxy profile so that it looks to be the solid line here. What happens is that all lensing observables, that is the image position, the image shape, the relative flux ratio, they're all invariant under this transformation to the surface mass density. However, the time delay distance scales as 1 minus kappa external, where this is the amount of sheet we're adding. This is problematic because all our cosmological information comes from the time delay distance. In order to break this degeneracy, two practical methods are to use stellar dynamics. So what stellar dynamics provides is a map at the effective radius. Gravitational lensing provides a robust measurement of the mass enclosed within the Einstein radius, which you see here. So both these two profiles will give you the same mass within this radius. If you have a different mass measurement at the effective radius, you can then, from dynamics, you can break the degeneracy between the two areas. Second approach is to study the external convergence by trying to get this quantity directly. For stellar dynamics, we have spectrum of the primary lens galaxy G1 from Keck, LRIS. From the modeling of the spectrum, we obtain that the stellar velocity dispersion of the primary lens galaxy is 260 plus or minus 15. For the external convergence studies, we have two approaches, both of which are based on the millennium simulations. And the first one is only the millennium simulation. I call it the MS approach. Here, what we do is we ray trace through the millennium simulation, identify lines of sight where strong lensing occurs at the redshift of our lens and source. We then sum up the external convergence along the line of sight, the strong lens line of sight, taking out the external convergence, excluding the strong lens line. This is following Shekwan and Hilbert's work, 2007. So by averaging over many lines of sight, we can build a distribution of the external convergence shown in the solid white curve. The dotted yellow curve is for all lines of sight. What you see here is that strong lens line of sight, if you exclude the strong lens plane, are not biased lines of sight. They're not very different from random lines of sight. This distribution is useful if we have a sample of lenses. However, it's not so applicable to our specific lens 1608 because, as we'll see, it's actually overdense. Recently, Chris Bosnack and Leon Koopman counted the galaxy number counts of strong lenses in an aperture of strong lenses and compared them to cosmos and also to random pure parallel fields. What they found was that 1608 has twice the average galaxy number count compared to cosmos. So now we use this information from observation. We again went into the simulation, identified lines of sight where the galaxy number count is twice that of the mean galaxy number count. And from those lines of sight, we get the distribution as is shown in white. This is now our most informative distribution of the external convergence. So we have multiple data sets for our cosmological measurements. We have the time delay, we have the lensing, we have the dynamics, and we have the external convergence study. How do we combine all of these together? follow a Bayesian approach. Let me first denote the cosmological parameters, pi, as h naught, omega m, omega lambda, and w. And denote c as all model parameters, which consist of cosmological parameters pi, and also non-cosmological parameters nu. This could be the slope gamma prime, and also capital external, for example. We're interested in the posterior probability distribution, probability of pi, cosmological parameters, given our three data sets, which is the marginalization of all model parameters, of the posterior of all, marginalization of non-cosmological parameters of the posterior probability distribution of all model parameters given the three data set. Where this thing here is given by the last line. Our base rule is the likelihood times the prior, and the likelihood splits up into three terms because our three data sets are independent. I don't want to go into the details of how we actually compute this likelihood. It is doable. What I'll focus on is the various forms of prior that we use. A key goal of this work is to identify and quantify the dominant systematic effects in time delay lenses, particularly 1608. And in order to do so, we assign well-motivated priors for each of the parameters and compare them quantitatively. So, for the cosmological parameters, we have three priors, KO3 uniform W. And the first one, KO3, this is Copeland et al., 2003. This is the most recent measurement of H0 from this particular lens before this work. They assume that omega m is 0.3, omega lambda is 0.7, W is -1, H0 is uniform between 0 and 150. This is also the most common cosmology assumed in the literature for using time delay lenses to measure H0. So this form of prior is considered for comparing to earlier work. The next one is uniform, where all four cosmological parameters are uniform in these ranges. We have two special cases, uniform open, where W is -1, and uniform W, where we assume flatness. Omega m is 1 minus omega lambda is 1 minus omega m. And finally, we have our most informative prior, W map 5. This is the 5-year W map result. We again have two special cases, omega W map open and W map W. For the slope of our power law profile for the galaxies, we again have three forms of prior. First one is uniform between 1.5 and 2.5. This is a very conservative range for the slope. This is our maximally ignorant prior. Next, more informative one is the SLAC. This is a Sloan lens ACS survey where they obtained 2.08 plus or minus 0.2. This result was based on an analysis of about 60 strong lenses using joint lensing and stellar dynamics modeling, by lens collaborators. And finally, our most informative one is the ACS prior of 2.08 plus or minus 0.03. This comes from the relative thickness of the arcs, as in our ACS images, because the relative thickness of the images, the arcs in the images, provide constraints on the slope. Finally, for the prior on the external convergence, again we have three. The first one is the maximally ignorant one, uniform, minus 0.25 to 0.25. And then we have the two that I described earlier, MS, based on strong lens line of sight, and an OBS based on number counting sources in the linear simulation. I will first investigate the impact of these two nuisance parameters on our cosmological inference. And to do so, I focus on KO3 cosmology. So recall that our most informative prior is the ACS for gamma prime, OBS for external convergence. In the left panel, I fixed the external convergence to be OBS and relaxed the prior on gamma prime. So with the 80th prior, H naught is 70.6 plus or minus 3.1. This is the red distribution here. If I relax it to flat, H naught increases by about 3 or 4. And that's shown in the blue distribution. And again, if I relax it again to the uniform prior, H naught doesn't really change. Also, the uncertainty doesn't really change. So the flux is actually not more informative than the uniform prior in this case. Nonetheless, if we look at just the uniform prior, the value of H naught is still within 7% of the HBS prior. So the impact of gamma prime, that is the slope, is relatively low on our cosmological instrument. Let us now fix the slope to be our most informative one, ACS, and relax the external convergence prior. So our most informative one, again, was 70.6 plus or minus 3.1 here. If we relax it to the MS prior, H naught increases by about 6. And then if we relax it to the uniform, it increases yet by another 6. And also the uncertainty more than doubles. You see the distribution here compared to that. You can see that our inference of H naught is actually limited by our knowledge of the external convergence. With our most informative priors on ACS and OES of 70.6 plus or minus 3.1, comparing to the earlier result, which is actually a significant improvement. Our uncertainty is reduced by more than a factor of 2, even after marginalization of the external convergence distribution.
So if you don't have priors on kappa external gamma prime, do you get uniform across?
No, these are the different priors.
Right. So what's this K03 prior and flat line across?
Oh, K03. This is uniform.
Uniform.
Yeah, this is this prior. So the dotted line is without 1608 beta. That's the constraint of the prior. It's called
Max
prior.
is white that you're constrained now.
Well, yeah, we're not. So the dotted line is without 1608. So it's purely just the prior. So H naught is uniform between 1 and 8. And the solid lines are with 1608. And then you see constraints from 1608 solid curves. Yeah.
So what's the typical redshift you're sensitive to, so your measurement? Maybe you said it before. But
So the redshift of our lens is 0.63, and the source is 1.4. Is that?
Yeah.
Okay. So this is a relatively restrictive prior. I mean, we fixed omega m, omega lambda, and w. So that is now relaxed from this restricted cosmological prior. And first question we ask is, well, what do time delay lenses really measure? From the beginning of my talk, it's the time delay distance. D delta t, as is defined here. Shown here is the 3 different cosmological priors, K03, uniform open, and uniform W. Dotted line is without 1608, and the solid curves are with 1608. So as you can see, without 1608, there's no constraint on the time delay distance, D delta t. But with 1608, all 3 curves give similarly peak distribution, independent of cosmology. So a good compression of this result is that we constrain the time delay distance to be a Gaussian distribution centered at 5226 megaparsecs with spread of 2.06. Well, no, 206, not 2.06. By construction of the time delay distance here, it is primarily sensitive to H naught and weakly dependent on other cosmological parameters. This is shown here, where if we focus on the blue curve, it's uniform open plus 1608. So omega m, the marginalized distribution of omega m and omega lambda shows a relatively flat constraint, but H naught shows a trusted peak distribution, indicating that the time delay distance is really more sensitive to H0. And the power comps is when we combine this robust measurement of the Hubble constant from 1608 with other experiments like WMAP. These constraint contours are shown in red. So combining 1608 and WMAP, we get the black contours where we break the degeneracy shown in the WMAP between H0, omega, and omega lambda. You can see in this plot we're actually constraining flatness. If we compare this to other cosmological probes, this is the table. WMAP 5-year result alone shows reconstraint on flatness, whereas the curvature parameter is 1 minus omega lambda minus omega m. WMAP plus key project, significant improvement in the precision. Supernovae, 2%. WMAP plus BAO, very tight constraint, 1.2%. And WMAP plus 1608, 2%. So you can see in the table, our 1608 is more informative when combined with WMAP than the HSC key project, and is comparable to those afforded by the current supernovae sample. If you look at this list, all the different kinematic probes show that the universe consists being flat. Now let us assert that the universe is flat and use all our available information to constrain dark energy. This is shown here. Again, the blue curve is uniform cosmology plus 1608. You see again that constraints of W and omega m is weak, but H0 is a sharply peak distribution. Combining this with WMAP in red, we get the black contours, which again break the degeneracy in WMAP. This is our joint constraints on H0 and W from 1608 and WMAP 5-year result. H0 is 69.7 plus 4.9 minus 5.0 kilometers per second per megaparsec. W is minus 0.94 plus 0.17 minus 0.19. Sorry? Is cosmological constant. So it's consistent with a vanilla cosmological constant. Let us now compare again to similar set of kinematic probes. WMAP alone provides weak constraints on H0 and W, 20 and 42%. With the key project, the uncertainty is reduced by a factor of 2. Supernovae gives very tight constraints, 2.3 and 6.5. EAO is 6.6 and 22. The recent reset-all differential distance ladder of the Hubble constant measurement, 5.0 and 12%. And this is our result of 1608 plus WMAP, 6.9 and 18%. So if we compare to this list above, we see that, again, it is more informative than the HSC key project, and it's actually comparable to the current BAO data in constraining H0 and W. So here is a summary of the first part of, future prospects. As I showed earlier in the talk, external convergence remains as the most significant systematic effect on H0. With many lenses, the contribution from the external convergence from line of sight should average out. This is shown by the MS distribution, where our straw lens lines of sight distribution of kappa looks very similar to random lines of sight. However, the external convergence from local overdensity that the lens directions may bias H0 because lens galaxies, like all massive galaxies, tend to live in overdense environments. If we have a sample of strong lenses, we would have to worry about the external convergence from local overdensity. 1608 is currently the only 4-image system with extended images for accurate lens modeling, and active time delay measurements with error of less than 5%. However, in the near future, LSST and pan-stars will discover hundreds of time delay lenses. And recently, Dan Cohen and Lexi Mustaka suggest that LSST plus Planck priors can actually reach sub-percent level in H0 and constrain W to 3%. caveats, provided that the systematic effects such as the external convergence are under control. And this is the main effort of our research on 1608, controlling these systematic effects. Several lens environment studies to model external convergence are underway. For example, Roger Blanford is actually trying to ray trace through the 1608 field to constrain the external convergence. Given all this, future samples of time delay lenses should be a competitive cosmological probe. And now, the summary of the first part of my talk. We have developed a comprehensive Bayesian analysis incorporating deep HSC ACS images, new velocity dispersion measurements, time delay data, and external convergence studies. Our inference on cosmological parameters is limited by our knowledge of the external convergence. 1608 provides a robust measurement of the time delay distance t, which is primarily sensitive to the Hubble constant. Combining with WMAP, 1608 constrains the curvature parameter to be this, a 95% confidence level, which is comparable to the current type 1 supernovae sample. And again, when combined with WMAP, 1608 measures this value for H0 and W, which are competitive to the current VO measurement. I'll go on now to the second part of my talk,